Now I will start explain about the heat transfer from the fin surface. So we know that when we want to transfer the heat from a surface to the surrounding, then we will get convection equation, which is H dA delta T, and the A actually stands for P delta S. The P is the peripheral area, means that it can depend on any kind of shape of the fin. For example, we can sum up all the sides of the fin and then we multiply with the delta x. We already involved the area that have released the heat, so we come out for equation 2. Rearrange all the equation and then we will get equation 3. And by taking the limit dx approach to 0, we can substitute the Q with the conduction from the pen wall, which is negative k a dt over ds. And after we rearrange them, actually we will get the m value, which is this one. And the general solution for this equation actually is this one. So that's how we come out the final solution for the fin equation for all the cases. So now I'm going to explain the first case, which is infinite long fin. So this case we have the long infinity fin, and here is dB and here is T infinity. And the temperature at the fin will always near to the surrounding temperature. And we substitute the boundary condition into this general solution, and we will get this C1 plus C2 equal to delta B, and also C1 equal to 0 and C2 equal to delta B. And for this, E minus infinity is always near to the 0. Substitute the L to infinity, and actually this one is small error. But to validate this equation, the C1 must be 0, and we substitute these two equations into the general equation, and we will get this equation 3.6. The first law of heat conversion, we know that the integral of HA delta T is equal to the heat rate. The delta A is P delta T delta S. The T infinity is this one. We get it from here, and we substitute this equation into here. After we rearrange, and we know that this actually is a constant, and we already need to integrate respect to x, so we just need to leave the x variable inside the integration, and after we integrate it is 1 over n, and then after substitute, then we get the equation 3.61. So for this case, we just add an insulator at the end of the fin. We can assume that there is no heat loss from the fin tip. The heat conduction is 0, and so dt over ds equal to 0. So for the second boundary condition, when s equal to 0, so is same goes to the case 1. We substitute into the general solution again. Since we have the d delta over ds equal to 0, so we must derive this general equation, and we apply the boundary condition. So we substitute equation 3 into equation 2. After we rearrange, then we will get a C1, and then we find C2. So then we substitute into general equation again. So we will get our equation 3.64. To simplify this type of equation, actually we use the hyperbolic equation, and we can simplify the equation into cos function. Adiabatic fin heat rate, and we know this one, the T minus T infinity, we get it from this equation, from the 3.64, and we substitute into this our HP and also TB minus T infinity, and also for the cos and L. So it's not related to the dx. After we integrate this, so we will get this sine ml, or after we substitute the limit, then we will get our final 3.65 equation. So for case 3, we assume that at the fin tip, we fix it with a specific temperature. Get the two boundary condition again, and use the general equation, and that we substitute the x to L, and we will get this C1. So we get C2 equal to delta B minus C1. After we rearrange, then we will get C2 and also C1. So then we substitute the C1 and C2 we get, and we will get equation 3.67. So for the delta T from this equation 3.67, and we will get 3.68. Now let's move on to the last case, which is the conversion from fin tip. The heat conduction from the fin is release the heat by the convection at the fin tip. Before this, we know that we have the first case when the T fin is equal to T infinity. And for the case 2, we know that the d delta and d x equal to 0. For the case 3, we set the T fin tip equal to some temperature, so we get the C1 and C2. For this case, we set it as the fin tip. We assume it releases the heat by the convection, so we get the first boundary condition and also the second boundary condition. So we substitute actually this delta x, we can get it from here, and we substitute here. After rearrange all the equation, we will get our first C1, and also we have a C2 here. So we must get rid of the C2, and we substitute the equation again and rearrange it. Then after we finally we get our C2 alone without the C1. C2, we get this one, the final one, with the simplified one, and we will get the C1. And after simplify it with the sine and the cos, and we will get equation 3.7. From the Fourier's law, we have HA delta T, and we get this equation from here, equation 3.7. We will assume that the length of the fin is from 0 to infinity, and we will get the final equation 3.71.